Hello and welcome to CodeWord. For all the people watching this video on YouTube, I would like to welcome you to our channel. This is CodeWord and we cover videos on computer science, both applied and theoretical, and I hope you will enjoy the channel. Please do check out other videos on the channel and be sure to check out previous videos of Rust programming series to get up to the speed of this video. Sorry for the late upload. I've been busy for, let's say, 3 weeks actually, and I'm going to be still busy throughout this March, so can't guarantee about the videos, but I'm here with this video, so let's get to it. I hope you watched all the previous videos in the series because we will be building upon those concepts. Let's talk about ownership in this video. Now, before we move on to ownership, we would like to cover a few topics which were kind of a review for all of you. Something like scope and other memory related stuff. Now, what is scope? A range within which a program for which an item is valid. Now, a scope is typically defined by curly braces and closed inner curly braces, and a scope generally means that the variable declared inside the scope will be valid up to the point where the closing brace is encountered. Let's just trace to this code to understand scope a bit better. When we are here, before the line where S was declared, S is obviously not accessible. Then the flow of program will move on to declare S, and now S is valid for throughout the scope until the closing curly brace is encountered. And when we are after the curly brace, S is no longer valid because its scope is over. Moving on from scope, we need to talk about stack versus heap. Now, stack is, as we all know, last in first out data structure. This is just a review for all of you. If you don't know what stack is and want to learn deeply about it, then you might check out other videos on other channels because we haven't covered it yet. And values are always removed from top and also added on top always. Sizes are known and fixed, and great when sizes are known at compile time. Now, what do I mean by that? Let's say you are currently inside a function. Now, this function is containing 3 integer variables which are declared locally. Now, compiler always knows what is the size of a data type, at least for primitive types. And let's say an integer costs around 4 bytes. And we have 3 variables, so 3 into 4 would be 12 bytes. So the top block would be of 12 bytes. And when we return from the function, we do this arithmetic of size multiplied by number of local variables and we get the final size. We take this final size and remove this much from top of the stack. Then we execute other code and eventually we call another function. Now, let's say this function is containing 2 integer variables, each of which is 4 bytes. So we need total 8 bytes. So we will create a block of 8 bytes and put it on top of the stack. This is how simply the stack works. Talking about heap, heap is always managed by operating system, and heap is actually an unorganized area in RAM which is given to the program dynamically. Whenever you ask for memory, OS returns a pointer to free memory block. Access is actually slow because we have to follow a pointer to get to the location where the memory is allocated for us. Let's look at it visually. Let's say that this is our memory. Each block is of 1 byte, and as you can see, most of the blocks are allocated and 2 blocks does not have anything in them, which means they are free. Now, when we say allocate 1 byte, let's say, the operating system goes to the memory and finds a free block for us. Actually, this is not how it works, but for our understanding purposes, it searches the memory linearly and then finds a block and allocates a pointer to it. Now, we can't just always keep allocating memory. We also need to deallocate memory. What if we never deallocate memory? What happens is we keep allocating memory and we have limited memory available in the computer. So we will allocate and then eventually we will run out of memory, and when we run out of memory the program will crash, which is definitely not what we want. So deallocating memory is absolutely necessary. Now there are two ways of deallocating memory, mainly two ways actually. These two are the most famous ones. First is garbage collection, which is used by languages such as Java, and other is manual memory management used by languages such as C and C++. And both of these approaches have their own problems. Let's talk about garbage collection first. Now, having a garbage collector is actually quite complex. Whenever we need to garbage collect, the program has to be stopped along with all of the threads of program. The garbage collector needs a complex algorithm to find out exactly which object is getting used right now and which objects are actually garbage. And most of the compilers actually need two passes over the memory to collect all the garbage. In first pass, they will actually mark the objects which are going to be removed in the next pass, and in the second pass they will actually free the memory. Talking about manual memory management, it is actually more problematic than garbage collection. Manual memory management was actually the reason garbage collection was invented in the first place. Now, if we try to manually manage the memory, programmer will forget to free some memory and leak some memory eventually around the program, which will lead to an quite untraceable bug, which is not good for us. A good design for memory management would be something which forces us to deallocate memory whenever required, rather than providing us infinite amount of flexibility. It will actually incur a lot of cognitive load on the programmer and will increase complexity of the program unnecessarily actually. Now, we don't want garbage collectors because they slow down the program. Rest is supposed to be fast, and we don't trust the programmers. What do? We actually take help from compiler, and that's where ownership comes in. Now we have three primary ways to manage memory. Now, before moving on to next sections, I will like to define certain assumptions that I'm making in this video, and these are general rules that are followed throughout all the good languages in the market right now. Primitive types are stored on stack, and dynamic, composite, and user defined types are actually stored on heap. Now keep in mind that there could be exceptions to these rules. There are lots and lots of languages out there, and new languages are being made every day, so there is nothing like a standard rule in the market of programming languages, but this is the rules that most of the languages follow, so we will make these assumptions in this video. So now at least we know that stack is not our problem. Stack is fixed, fast, and works flawlessly. Our problem is heap, and most of the data types that we have looked up till now are actually stored on stack. Integers and floats, booleans, doubles, all the data types are primitive and are stored on stack. Let's look at a type which is actually stored on heap. It is the string type. It is a dynamically growing string, and it is actually stored on heap, as I said. We'll look at a snippet of code to understand really what is going on. Look at this code. It is allocating a string from a string literal called hello and assigning the pointer to s. Now this memory is actually allocated dynamically because the string can grow and or shrink according to our program requirements. Variable is not usable after the scope is over, that is after the curly brace, and it should be freed, as logical as it seems. Now we don't trust the programmer to call a special kind of function for us to free the memory, and we don't have garbage collector. And so to take help from the compiler, what the compiler will do is it will go through our code and check all the variables that are supposed to be freed after the curly brace. What it will do is it will sneak in a little function call before the curly brace to free our variable s, and it is called drop. It will call s.drop, which will actually free all the resources that were held by s. Now this is all good and fine, but what if we do something like this? We have this old code, and what we do is we take another variable s2 and assign it to s. The pointer of s will be put into s2 now, and both of the values are pointing to the same memory location in the RAM. Let's look at this visually. there is string in memory hello 0 1 2 3 4 are all the blocks that it requires, and we are passing it the pointer to variable s, which will look something like this. Then we will go ahead and declare s2. We will pass the pointer of s to s2, which will make essentially both of the variables point to the same location. Now compiler will analyze the block of code and we'll see that we need to free two variables s and s2, so it will also call s2.drop, but it will actually mean a bit of problem for us. When the function block is over, it will call the functions and the functions both will try to free the same memory. This problem is actually called double free error, and it leads to a really well-known phenomenon in computer science called memory corruption, which is definitely bad, as you might know. What is the solution then? Ownership to the rescue. Now ownership actually works on a few simple rules. First rule is each value in Rust has a variable that's called its owner. Essentially what it means is if there's a memory location in the RAM, then each memory location in the memory must be pointed by a unique variable which is called its owner. There can be only one owner at a time. That's as I said, to avoid double free error problem. And when the owner goes out of scope, the value will be dropped. Seems simple. Let's apply all these rules to the previous code. As we saw, this was the situation before s2 was made to point to the memory location of hello. Now as you can see, both the variables are pointing to the same memory location, which is not good. What the compiler will do is it will break the connection of s, as the s2 is actually pointing to the memory location and it is the newer variable. We pass the ownership of string hello from s to s2 when we say s2 equals s. The connection will be broken and s will also be considered as invalid. As you can see now, only one variable is pointing to the memory location, and when the block is over, it will try to free the memory by calling drop. Seems fine. But having this kind of behavior has some interesting implications. Let's look at those. Look at the following code, which is a simple main function and another function called die. When the first line is executed, the scenario in memory is something like this. Hello will be allocated on RAM and the pointer to it will be passed to s. Then the code will execute and we'll call the function die with the parameter s. The flow will come to the declaration of die function and it will see that s2 is the parameter name that is passed into the die function. Now as we passed s, the ownership of s will move to s2. So now s2 will point to the memory location and s will be considered invalid. The connection will be broken and s2 is the only owner now. The code will continue to execute. It will print the value of s2 and then the function will be over. When the function is over, the compiler will think that s2 is the owner and it is no longer usable after the function is returned. So it will call drop on it. What it will do is it will drop s2 along with the memory location hello. The function execution flow will return to the main function and it will try to call s.push. But as you can see, s is invalid and hello is not actually in memory. This will actually confuse the runtime environment and panic will set in. Now you should keep in mind that if you write this code in a Rust file and try to compile it, the Rust compiler will not actually let you compile this kind of code because, as I said, Rust is designed to be safe and this is not a safe behavior. Now Rust has its own way of dealing with these problems and we will take a look at them in the later videos, but I'll leave this as an exercise to you. What can I add to the die function which will still allow us to use the variable s in the function main even after the scope of die function is over? That's it for today's video and thank you for coming in. If you liked the video, please hit the thumbs up button subscribe to my channel and share this video to all of your friends. Peace.